Hello everyone, today I'll be presenting my paper, Active Probing and Influencing Human Behaviors via Autonomous Agents. My name is Shuangge Wang. I'm from the Ming Department of Electrical and Computer Engineering from University of Southern California. This paper is a joint effort by me and Yiwei Liu and John M. Dolan from the Robotics Institute at Carnegie Mellon University. So to motivate this work, why do we want to influence and probe human agents? Well, generally speaking, humans are less informed and more egocentric and suboptimal at times compared to autonomous agents. Autonomous agents are better equipped to modulate the entire system, and that's what we want to empower them to do in this paper. So in a human-robot joint systems, the autonomous agents possess some sort of human model, usually achieved by inverse reinforcement learning or maximum entropy learning techniques. These models, although generally reasonable, fall short when interacting with specific humans in close proximity, which is why we need an on-life probing procedure to reduce uncertainty of the human model in an active manner. This research focuses on how to actively probe a human agent, and leveraging on that probed information, how could we influence human agents for some designated objectives? So first, we introduce a passive update procedure. So basically what we're doing here is we have a set of candidate profiles, phi 1, phi 2, all the way to phi m, and the autonomous agents possess some sort of belief over this phi. And at every time step, the autonomous agents asks, which is the most likely profile to execute the observed control? And we do this iteratively at every time step. However, this is a passive technique, meaning that there's no exploration in this passive update technique, which is why we need to introduce an active probing procedure. So in this active probing procedure, the autonomous agent optimizes to reduce the maximum amount of entropy over the belief at every finite horizon, so that it will reduce the uncertainty of the belief, so that it will be more convicted to, and the belief will cluster to a certain region. And then by the end of the probing procedure, it would have a peak belief, say phi, and then based on that phi, the autonomous agent could design an objective function to optimize, for instance, for better efficiency and better optimality. For applications, we simulate two autonomous driving scenarios. So in the first one, what we're trying to do is we're trying to influence human drivers who with intentions to drive faster to inner lanes, here shown as left lanes. So what the autonomous agent does is it'll first probe the desired velocity of the human vehicle. If it intends to drive faster than some cutoff, then the autonomous vehicle will influence the human vehicle to merge via the widest gap among the wide vehicles. So here we can see it is actually slowing down to force the human vehicles to merge via the widest gap. So here we have a comparison between a passive and an active updating procedure. So we can see that not only the active updating procedure is more precise, which is more closer to the ground truth of 25 meters per second, which is the desired velocity of the human's vehicle, humans intend to travel. It actually has a less of an entropy, about 1 bit of information, meaning that it is less uncertain about this human model compared to a completely passive approach. And based on that information, the human vehicle could slow down to force the autonomous vehicle, to force the human vehicle when it seizes an opportunity that the human vehicle could merge. And we can see that by influencing the human vehicle to merge, the human vehicle actually experiences a 25% increase in its velocity, which is optimal for the desired efficiency. Also, this influencing technique has underlying safety implications, because traveling faster at an inner lane is actually safer because there are less vehicles coming in and out of the lane frequently. On the right-hand side, we can see that the cumulative control deviation for the backbone vehicles is about 25 meters per second, meaning that our perturbations is bounded. Here, for the second scenario, we consider a lane switching scenario where the right lane is about to come to an end, probably because of obstacles or traffic, or simply just because we're transitioning from an urban environment to a highway environment, so that the autonomous vehicle and human vehicles need to switch. However, consider the fact that all the gaps are just too narrow for humans, but the autonomous vehicle is intricate enough to maneuver. So what the autonomous vehicle is going to do is that it will first probe the desired headway of this human vehicle, and then it will merge first, slow down to create enough gap for humans, and then the humans, based on the probe headway, and then the humans could merge with ease. So we can see here is the same belief comparison. Even though the precision is pretty much the same, we can see that the uncertainty is definitely not. In fact, the active approach actually has about 1.5 bits less of entropy, meaning that it is more confident about its current belief. And based on the probe headway, the autonomous agent could merge first and slow down and create the gap for human vehicles to merge. And here we use a adaptive cruise control to simulate as a baseline where autonomous vehicle is actually passive, so that autonomous vehicle and human vehicle will actually have to wait until all the white vehicles have passed to switch. And we can see that the velocity deviation is actually 2.5 times larger than the velocity deviation in an influence approach for the background vehicles. And the cumulative control deviation for the autonomous vehicle and the human vehicle is actually almost twice as large as the cumulative control of the background vehicles. So in this case, it is actually more optimal for the autonomous vehicle and human vehicle to merge in this case. Moreover, our approach is actually agnostic to the number of white vehicles in the background. Therefore, if there are more white vehicles in the background, then the cumulative control deviation and the velocity deviation would continue to increase. And this is the entirety of my research. I would like to give a special thanks to Yiwei Liu, John M. Dolan, and Rachel Burson for their awesome support and hospitality and CMU. And I also like to thank Argo AI Center and the entire 2022 Robotics Institute Summer Scholar cohort. Thank you very much.